let's solve some problems. So here's the first problem. If alpha is the cube root of 2, find the irreducible polynomial of 1 plus alpha squared over q. So if alpha is cube root of 2, then what we know is that the irreducible polynomial of alpha is t cubed minus 2, right? Alpha satisfies t cubed minus 2, and t cubed minus 2 is clearly irreducible over q because it has no roots over q. A cubic polynomial cannot be irreducible unless it has a root. So alpha satisfies t cubed minus 2, and so q alpha is just qt mod t cubed minus 2, which means that 1 alpha and alpha squared are linearly independent over q. Okay. So with that in mind, let's say gamma is 1 plus alpha squared. We want to find a polynomial, which an irreducible polynomial that gamma satisfies. So the strategy for all these problems, so basically if you have a polynomial, say gamma satisfies a polynomial like gamma to the 4 minus 3 gamma squared plus 1 equals 0, then essentially this, if you think of gamma squared, gamma cubed, and also 1 as elements of q alpha, then you can think of them as vectors and expand them in the basis 1 alpha and alpha squared. And this kind of equation is a linear relation between those vectors. So the idea is we start with gamma, and we could even take 1, so that's just 1, and we can think of these as vectors when we expand them in terms of 1 alpha and alpha squared. So we just compute some powers of gamma and then look for the first time those vectors become linearly dependent. So in terms of the coordinates 1 alpha alpha squared, this has 1 0 0 coordinates. This has coordinates 1 0 1. What about gamma squared? Well, it's 1 plus 2 alpha squared plus alpha to the power 4. So this has coordinates, alpha to the power 4, we know that alpha cubed is 2, so this is 1 plus 2 alpha plus 2 alpha squared. So this has coordinates 1 2 2. And let's look at gamma cubed. This has coordinates, okay, so far these vectors look like they're linearly independent, right? But if you take gamma cubed now, then we get that gamma cubed is 1 plus 3 alpha squared plus 3 alpha to the power 4 plus alpha to the power 6, which is 3 alpha squared is 6, 3 alpha to the power 4 is alpha cubed is 3, so this is 3 into 2 6 alpha, and alpha cubed is 2, so alpha to the power 6 is 4, so we get oh, I'm sorry, 3 alpha squared is not 6, it is just 3 alpha squared. Alpha squared is not 2, right? Alpha cubed is 2. So what we get is 5 plus 6 alpha plus 3 alpha squared. So this has coordinates 5 6 and 3. So now we look at these 4 vectors. They must have a linear dependence because they are vectors in q cubed. So let's just figure out how to write gamma cubed, expand gamma cubed in terms of 1 gamma and gamma squared. Now if you look at these coefficients here, so if you look at the second coordinate, for example, so the second coordinate here is 2, here it's 0. So the only way, so we are looking for a relation of the form a1 plus a2 times gamma plus a3 times gamma squared is equal to gamma 3, gamma cube. So if you look at the second coordinate, the only possibility is that a3 is 3, so this has to be multiplied by 3, and once you do that, this becomes 6. But now let's look at the third coordinate. So if I do 3 times this, I get 6 here, and so I have to subtract 3 times 1 to get 3 back. So I have to do this times minus 3. Okay, and but then when I do that, this 3 times 1 and minus 3 times 1, they cancel out, and so to get 5 here, I have to do 5. So anyway, one way or the other, I find out that gamma cube is equal to 5 minus 3 gamma plus 3 gamma squared. And so the irreducible polynomial of gamma, which is just 1 plus alpha squared, is t cubed minus 3t squared plus 3t minus 5. And that's your solution. Here's the second problem. Find the minimal polynomial of square root 3 plus square root 5 over q. Before we jump into the calculation, let's just note that square root 3 does not belong to q adjoint square root 5. Because we know that this q adjoint square root 5 consists of complex numbers of the form a plus b root 5, where a and b are rational numbers. And it's not difficult to show. So if you have a number like this, it's square a plus b root 5 squared is going to be a squared plus 5b squared plus 2ab root 5. And if you want this square to be 3, then you would need either a to be 0 or b to be 0. In fact, for this square to be a rational number, you would need either a to be 0 or b to be 0. Otherwise, this 2ab root 5 term will come to haunt you. But if a is 0 or b is 0, then you cannot have. So if for example, if a is 0, then you're looking at b root 5 squared, which would be 5b squared. But 3 is not a multiple of 5. So it cannot be that b root 5 squared is 3. And similarly, of course, a squared cannot be 3 because a is a rational number and square root of 3 is irrational. So we know that square root 3 does not lie in q adjoint root 5. And very similarly, we know that square root 5 does not lie in q adjoint root 3. What this means is that 1 alpha, so let's give these names. So let's say alpha equals let's call this alpha square root 3 and beta square root 5. So 1 alpha, of course these are linearly independent over q. 1 and beta are linearly independent over q, but alpha and beta are linearly independent because beta is not in q root 3, not in the field obtained by adjoining alpha to q. And again, alpha beta is linearly independent of both alpha and beta because alpha beta is neither in q root 3 nor in q root 5. It's not in q root 3 because alpha is in q root 3 but beta is not in q root 3. So alpha beta cannot be in q root 3. So these are linearly independent. So this is linearly independent set. And so now we take gamma to be 1 plus alpha squared, and just like last time, we start computing powers of gamma. So and we expand those powers in terms of the spaces. So firstly we take the 0th power. So 1 is equal to 1 in terms of this basis. It corresponds to the vector 1 0 0 0. And now let's look at gamma. This is just alpha plus beta. So this is the vector 0 1 1 0 in terms of this basis. Gamma squared is alpha squared plus beta squared, which is 8 plus 2 alpha beta. So this corresponds to 8 0 0 2 in this basis. And you can see so far these vectors are all linearly independent. And let's look at gamma cubed. It's 8 plus 2 alpha beta into alpha plus beta. So what we get is So let's just do some rough work here. 8 plus 2 alpha beta into alpha plus beta, that works out to 8 alpha plus 8 beta. Now 2 alpha beta into alpha is 2 alpha squared beta, but alpha squared is 3, so that's 6 beta. And 2 alpha beta into beta is 2 alpha beta squared, but beta squared is 5, so this becomes 10 alpha. So what we get here is that this is 18 alpha plus 14 beta. And this again, see, these vectors are very nice. They either have non-zero coordinates in the two middle coordinates, or as in gamma and gamma cubed, or they have non-zero coordinates in the first and last coordinates, as in 1 and gamma squared. So it's very easy to see that these are linearly independent. You just check that this vector and this vector are linearly independent, this vector and this vector are linearly independent. Obviously all four of them are linearly independent. What about gamma to the power 4? So we have 18 alpha plus 14 beta. Let's just use this space here to do the calculation. 18 alpha plus 14 beta into alpha plus beta. So what we get is 18 alpha squared, but alpha squared is 3, so that's 18 into 3, which is 54, plus 14 beta squared, so beta squared is 5, so 14 into 5, that's 70, plus 18 alpha beta plus 14 alpha beta, so that's 18 plus 14, which is 32 alpha beta. So 54 plus 70, that's 124. So we get 124, 0, 0, 32. So these are the first 5 powers of gamma, starting with gamma to the power 0. And now we can find a linear dependence between these vectors. Now this gamma to the power 4, we want to express it as a linear combination of 1 gamma, gamma squared and gamma cubed. Well, the two middle coordinates of gamma to the power 4 are 0. So we only need to worry about, we will only use these two vectors in our expansion, right? We will only use 1 and we will use gamma squared. Okay, and luckily for us, here this coordinate is 0. So we know that this vector gamma squared must occur 16 times to get this. But if this occurs 16 times, then here we have 8 into 16. What's 8 into 16? So 16 into 4 is 6, so that's 128. So we would have 124 minus 128, and so we'd have to we'd have 128, so we'd have to subtract 4, so this into minus 4. So what we get is gamma to the power 4 equals 16 gamma squared minus 4. Therefore the minimal polynomial, the irreducible polynomial of 1 plus alpha squared is 16 t to the power 4 minus 16t squared plus 4. That's the solution. Now I'm going to take the previous problem and change it just a little bit. Firstly, instead of problem 2, I'm going to call it problem 3. And instead of finding the minimal polynomial of root 3 plus root 5 over q, I'm going to ask for the minimal polynomial of root 3 plus root 5 over q square root 15. So now this is actually our old alpha beta. So alpha beta is no longer linearly independent of 1 and alpha and beta, because alpha beta is already in the field. So alpha beta is a scalar. Okay, so what we do is we go back to the previous problem and we look at these powers, but now what we have is alpha beta is over here. So let me just copy this whole thing. and bring it over to the next slide page. Okay, so these are the calculations in Q, but now this alpha beta is part of the first coordinate, so we no longer have this third coordinate, and this rather fourth coordinate. And so what we are saying is that this is 1 0 0, this is, well, still alpha plus beta, but this was 8 plus 2 alpha beta. So what we get is, here we would write 8 plus root 15, because now that's in the field. Okay, but this gamma squared is already now a scalar multiple of 1 0 0. So these two steps we don't need at all. So we don't need this bit here. So we'll just remove it. And so what we get is gamma squared. Since we are working over q root 15, we get gamma squared is 8 plus root 15. And so what we have is that the minimal polynomial of root 3 plus root 5 over q root 15 is t squared minus 8 plus root 15. And that's the solution. I'm sorry, this should be, I think there was a 2 there, right? Yeah, that's a 2. So this should be 2 root 15. Let me just, oops. 8 plus 2 root 15. And so this should be 8 plus 2 root 15. And that's the solution to our problem. Okay, now come to problem 4, which is a very interesting class of numbers whose minimal polynomials we shall seek. Let zeta n be e to the power 2 pi I by n. So this is a complex number, and if you raise this number to the power n, then you get 1. So this is called a primitive nth root of unity. The powers of this number are all the nth roots of unity in the complex numbers. All the numbers which, if you raise to the power n, you get 1. And a very interesting problem is to determine the degree q zeta n over q for so this is known for all n, but today we'll just do n equals 1, 2, 3, 4, 5, 6. So we'll try these. We may not succeed in solving all of them with what we know right now, but let's give it a shot. So what is zeta 1? So zeta 1 is just 1. It's a rational number. So q zeta 1 over q has degree 1. In fact, the minimal polynomial, the irreducible polynomial of zeta 1 is just t minus 1. Zeta 2 is minus 1. Again, it's rational. So q zeta 2 over q is equal to 1. What about zeta 3? So zeta 3 turns out to be, it's e to the 2 pi I by 3. It's a cube root of unity. So it satisfies the polynomial t cubed minus 1, which is t minus 1 into t squared plus t plus 1. But of course we know that t minus 1 doesn't vanish at zeta 3. So t squared plus t plus 1 must vanish at zeta 3. And t squared plus t plus 1 is irreducible over q. So this must be the irreducible polynomial of zeta 3. And so this part is irreducible. And satisfied and vanishes at zeta 3. So what we get is that q zeta 3 over q is just 2. This is the irreducible polynomial. Let's look at zeta 4. So zeta 4 is e to the 2 pi I by 4, which we also know to be the number I, the square root of minus 1. And this satisfies t to the power 4 minus 1, which I can write as t minus 1 into t plus 1 into t squared plus 1. Now these factors do not vanish at zeta 4. So we are only left with this factor, and this is irreducible again. So for quadratic polynomials, it's easy to check that they are irreducible. You just use the formula for the root of a quadratic polynomial. If the discriminant is negative, then they are irreducible. So this is irreducible, and so again we get q zeta 4 over q is equal to 2. Okay, and now let's go to zeta to the power 5. So zeta power 5 is e to the 2 pi I over 5, and this satisfies t to the 5 minus 1, which I can write as t minus 1 into t to the 4 plus t squared plus t plus 1. Now t to the power 4, sorry, there's one more term missing, plus t cubed plus t squared plus t plus 1. And it turns out that this polynomial is irreducible, but showing that it's irreducible may not be that easy. I will defer it to next week, and you will see this when we prove Eisenstein's criterion for irreducibility. But anyway, it turns out that this guy is irreducible, and in any case zeta 5 doesn't satisfy this. So this is to be done. So we haven't technically fully solved this problem. You can try proving that it's irreducible with how much you know right now, like by looking for a factorization. We know it has no roots, but we need to know that it doesn't have any quadratic factors. So you can try to do that with your bare hands. It comes out more easily with Eisenstein's criterion. So this needs to be shown to be irreducible. But then if we accept the fact that that is irreducible, then what we get is q zeta 5 over q has degree 4, because this polynomial is of degree 4. An interesting one is zeta 6 e to the 2 pi I by 6. So this satisfies t to the power 6 minus 1, and this has a nice factorization. So it's t cubed minus 1 into t cubed plus 1, but t cubed minus 1 is t minus 1 into t squared plus t plus 1, and then there's another thing which is t to the power 4 plus t squared plus no, that's just t cubed plus 1. Sorry. Okay, so these two give t cubed minus 1, and this is t cubed plus 1. T cubed minus 1 into t cubed plus 1 is t cubed minus 6. Now this does not vanish at zeta 6. This also does not vanish at zeta 6. We know what its roots are. Its roots are zeta 3 squared. So this doesn't vanish at zeta 6. So this must be so this polynomial vanishes at zeta 6, and this polynomial is irreducible. Again, for a cubic polynomial, we know it's irreducible if it doesn't have a root. So this guy is irreducible, and so what we get is that the degree of q zeta 6 over q is equal to 3. Okay, so we have an interesting sequence here: 1, 1, 2, 2, 4 and 3. See if you can guess what the pattern is. This is a very important class of field extensions. These are the cyclotomic extensions, and we will keep revisiting them during this course. A last problem: prove that a regular pentagon can be constructed using a straight edge and compass. No, you can construct a regular pentagon if you can construct a fifth root of unity. So let zeta 5 as before be e to the 2 pi I by 5, and if you can show that this point is constructible, then its powers will also lie in the same field q adjoins zeta 5, and you can realize a regular pentagon as having corners given by the, so if I draw a regular, it's not a great drawing, let's try to improve it a bit. Okay, this is the best I can do. So this is 1, this is zeta, this is zeta squared, this is zeta cubed, and this is zeta power 4, and these will all have the same angle relative to each other at the center. So this will be a regular pentagon. So we just need to show that we can construct the point zeta is constructible, and then its powers will automatically be constructible by our criterion for constructibility. So we need to show that zeta 5 is constructible. Well, we've already seen that zeta 5 probably has degree 4 over q. It satisfies a polynomial of degree 4 at any rate. So let's just see that. So in fact, we have zeta 5 satisfies t to the power 4 plus t cubed plus t squared plus t plus 4. Over q. And to show that it is, so the degree of zeta 5 is 4. Q adjoint zeta 5 is probably 4. Well, we haven't quite proved that, but it will become clear by the time I solve this problem. So what we have is this, we have this q zeta 5. Zeta 5 doesn't satisfy any quadratic polynomial over q. So what we are asking is, can we find a field here f between q zeta 5 and q, such that f is of degree 2 over q and q zeta 5 is of degree 2 over f. So zeta 5 is constructible if and only if we can find this f such that this holds, i.e. f lies between q zeta 5 and q, and f is degree 2 over q and q zeta 5 is degree 2 over f. So we're looking for this kind of a field. So in this field, since this is a quadratic equation, zeta 5 would satisfy a quadratic polynomial over f. So what we would try to do is take this polynomial of degree 4 and see if we can write it as a product of two quadratic polynomials over some intermediate field. So we would have to factorize t to the power 4 plus t squared plus t cubed plus t squared plus t plus 1. And we want to factorize this. We would have two quadratic factors, and let's just try this with t squared plus alpha t plus 1 and t squared plus beta t plus 1. Let's try to find a factorization like this. And alpha beta need not be rational numbers, they just need to lie in a quadratic extension of alpha of q. So if we expand this, what we get is t to the power 4, then the coefficient of t cubed is alpha plus beta t cubed, and then the coefficient of t squared is 2 plus alpha beta t squared, right? And then the coefficient of t is again alpha plus beta t, and then plus 1. So what we need is alpha plus beta is equal to 1 and 2 plus alpha beta is equal to 1. Well, 2 plus alpha beta is equal to 1 is the same as saying that beta is minus alpha inverse. And substituting that in here, we have alpha minus alpha inverse is equal to 1. Multiplying by alpha and bringing everything to the left hand side, we get alpha squared minus alpha minus 1 is equal to 0. Which means that alpha has to be 1 plus or minus square root 5 over 2. 1 plus square root 5 over 2 is the golden ratio. This is a very, very famous quadratic equation. And well, so beta, so maybe we can take alpha to be 1 plus square root 5 over 2, and we can take beta to be 1 minus square root 5 over 2, and you'll find that all your conditions are satisfied. So what we get is t to the power 4 plus t cubed plus t squared plus t plus 1 is equal to t squared plus 1 minus root 5 over 2 t plus 1 and t squared plus 1 plus root 5 over 2 plus 1. So what we have is, now the field generated by 1 plus root 5 over 2 contains 1 minus root 5 over 2, and the field generated by 1 minus root 5 over 2 contains 1 plus root 5 over 2. So these are the same field, and so what we have is that zeta 5 satisfies the quadratic equation t squared plus or minus one of these equations, 1 over root 5 by 2 plus 1. So maybe it satisfies one of these over q adjoint root 5. So that's our intermediate field, q adjoint root 5. So we have q zeta 5 lies over q adjoint root 5 lies over q, and each of these is of degree 2, and so zeta 5 is constructible. It's a constructible point, and hence a regular pentagon is constructible. Now it would be an interesting project for you to take this idea and try to translate it into an actual straight edge and compass construction for a regular pentagon. So I hope you have fun doing that, but I'll just leave you with this challenge for now.